Kepler's second law of planetary motion. Every planet moves around the sun in an elliptical orbit. Now, for the explanation of second law, we consider a radius vector from sun to earth, the line joining the sun to planet. This line we considered as radius vector. Now, the planet travels for some distance in a finite time and reaches this position. When the planet comes to Earth, the radius vector is this one. This is the radius vector. In this finite time, it covers an area A1 with respect to the sun. That area is represented with this shaded part as A1. Similarly, when the planet comes to this position, the line joining the sun and the planet, we call it as radius vector, that is this one. This is the radius vector. Now, in finite interval of time, here this radius vector means planet moves from here to some position like this. Then the radius vector is this one. This radius vector again covers some area that is represented with A2. According to Kepler, if the time intervals are same, since the time taken by the planet is same, their area covered is also same. So, to move from here to here, the planet takes some instant of time. In the same instant of time, planet moves from here to here. So, here to here time taken, here to here time taken, both are same. That's why the sweeping areas A1, A2 also same. The radius vector drawn from the sun to any planet sweeps out equal areas in equal interval of time. This is the Kepler's second law. What second law states? The line joining the sun and planet, we call it as radius vector. The radius vector drawn from the sun to any planet sweeps out equal areas in equal interval of time. This is the Kepler's second law of planetary motion. This law is also known as areas. Why? Because here area covered by the radius vector is explained by this law. That's why this law is also known as law of areas. This law of areas can be understood as consequence of law of conservation of angular momentum. The law of conservation of angular momentum is valid for central forces. What are central forces? Central force means, one of the example of central force is gravitational force. Gravitational force is the central force. Here also, in between the earth and the sun, or planet and the sun, that is the gravitational force, is a one kind of central force. What is meant by central force? The central force is a force always act along the line joining the centers of the two objects. Gravitational force act similarly like this. That means the gravitational force is central force. The central force is that force on a planet which is along the vector joining, that we call as line joining the sun and the planet. Now, proof of law of areas. A planet moves in an elliptical orbit from position A to B in a time of delta t. When the planet is at A, the line joining the sun and planet, the radius vector is r bar for time interval t. Now, the planet moves from A to B. Now, the radius vector is r of t plus delta t. Why? Because for the movement of planet from here to here, planet takes delta t time. The finite time is here delta t. During this delta t time, the planet moves from A to B. So here, what is this radius vector r? This radius vector r for the time instant t plus delta t, and F is the gravitational force between the planet and the sun, and here the angular displacement is delta theta for planet moves from A to B. For planet moves from A to B, the angular displacement is delta theta. That delta theta is this one. This is that delta theta. Now, when the planet moves from A to B, observe here, this part is an arc. Here the angle is delta theta. From the definition of plane angle, delta theta is equal to angle equal to arc length by radius. Arc length by the angular displacement of the planet for delta t instant of time, that is delta theta is equal to arc length by radius. From here, what is arc length? Arc length is angle into radius. Arc length is AB here. That AB is equal to angle into radius. Radius is R into angle is delta theta. So, this is the AB length. Now, when the planet is at A, its radius vector is R. It moves to B point. Area covers delta A is equal to, it is similar to triangle shape, half into base into height. Here base is this part R delta theta and the height is radius vector R. That means delta A. What is delta A? Area covered by the planet in delta T time. That is delta A is half into R delta theta into R, which is equal to half into R square delta theta. Now, both sides divided with delta T, delta A by delta T, which is equal to half R square into delta theta by delta A. But delta theta by delta T. What is delta theta by delta T? Change in angular displacement with respect to time. We call it as rate of change of angular displacement. That is angular velocity omega. That means delta A by delta T equal to half R square. In place of delta theta by delta T, we are using omega. Means half R square omega. The angular momentum of a planet of mass m is L equal to I omega. What is I there? I is moment of inertia. So, I is for planet mr square. M, mass of the planet. R is its radius from the sun. Radius vector with line joining the planet and sun. That is the radius vector. L equal to mr square omega. From here, omega is equal to L by mr square. So, bring this mr square to here. Then L by mr square is omega. Now, delta A by delta T, which is equal to half R square omega. In place of that omega, we substitute L by mr square. Then the equation changes like this. Delta A by delta T is equal to half R square L by mr square. Here R square gets cancelled. This R square. What left now? L by 2m. 2 is a numerical value. M, mass of the planet, which remains constant. 2 is constant, m is constant. L, angular momentum, which is also constant, means delta A by delta T or dA by dt is a constant. What is dA by dt? dA by dt is the aerial velocity of planet, which is constant. We proved that the planet covers the line joining the sun and the planet. We called it as radius vector. Sweeps out equal areas in equal interval of time. That is the second law of Kepler. Angular momentum L is constant. L formula is mvr. Angular momentum L is equal to m into v into r. mvr for perihelion point and aphelion point. Any point like this in the elliptical orbit, when the planet moves around the sun, sun is at here, the planet is at here. So then for two different positions, the two different positions are aphelion and perihelion. So for these two different positions, L remains constant. L equal to mvr, m also constant. LMR constants means VR is equal to constant. VR is constant means V is inversely proportional to R. VR is constant means V is inversely proportional to R. Aphelion radius and perihelion radius. Aphelion is the farthest point from the sun. That means this is a planet. I indicated it as planet P. Now it is aphelion point, and very close to the sun, this point, this is perihelion point. Aphelion point to sun distance, this is taken as RA. Perihelion point to sun distance is taken as RP. Here RA is greater than RP. RA is greater than RP, and what is V and P relation? Velocity is inversely proportional to R. V is inversely proportional to R. Means RA greater than RP means VA is less than VP. VA is less than VP. Is the speed of the earth more at perihelion than at aphelion? Yes. The speed of earth at perihelion is more than aphelion. Why? Because perihelion point is the closest point. Some MCQs. Which law states the line joining the sun and the earth sweeps out equal areas in equal interval of time? Usually the options are Kepler's first law, second law, third law, and law of gravitation. Kepler's second law is the answer. Why? Because the line joining the sun and earth, nothing but radius vector, sweeps out equal areas in equal interval of time. Earlierly we observed that proof of this second law also. The radius vector drawn from the sun to any planet sweeps out equal areas in equal interval of time. So Kepler's second law is that one. Next, the motion of planet in the solar system is an example of conservation of angular momentum. Why? Because L equal to mvr, which remains constant. Means for perihelion and aphelion points, the speeds are different. So that means the motion of planet in solar system is one of the best example of conservation of angular momentum. Thank you.